If you recall from previous lessons, distance and displacement are scalar and vector counterparts. In the same way, speed and velocity form a matching pair. So far, we have analysed distance time, displacement time, speed time, and velocity time graphs. This lesson will focus on acceleration time graphs only, because acceleration has no scalar equivalent. Before diving further into physics, let's check up on Lotus Lang. She's busy hunting the people behind a missile launch, and her latest lead has brought her to the Lexicorp tower. With the help of her government clearance, Lotus arranges a private tour. Dylan welcomes her in the foyer and provides her with an information booklet highlighting the company's services. But first, she makes a request. She'd like to inspect the communications antenna on the top floor. With a polished and professional smile, Dylan ushers her into the glass elevator. Upon arriving at the top of the Lexicorp building, Lotus scans the antenna for bugs. She doesn't want to discuss classified information if spies have tapped the network. While Dylan isn't watching, Lotus examines her surroundings. She spots the helicopter from yesterday, and it's owned by the neighbouring country, Anchuria. What could they be planning? Satisfied with the building's cybersecurity, Lotus and Dylan step back into the elevator. This time, they speed down towards the 12th basement level, where top-secret experiments are conducted. Let's pause here to introduce the acceleration time graph. This is used in physics to show the motion of an object, with acceleration on the vertical axis and time on the horizontal axis. Since acceleration is a vector, negative values are possible. This particular graph shows the motion of Lotus and Dylan in the elevator. Up is the positive direction, so down is negative. After the doors close, they accelerate at -1 metre per second squared up. The acceleration is negative because they speed up in the negative direction. Shortly afterwards, the lift stops accelerating. It travels down the building with a constant speed of 10 metres per second between 10 and 28 seconds. From 28 to 38 seconds, the acceleration is positive because the lift transitions from moving down to stationary. They arrive at the 12th basement floor after a total of 38 seconds. As we can see, the lift's acceleration changes over the entire journey, making this an example of non-uniform acceleration. When analysing acceleration time graphs, any increasing or decreasing trend indicates non-uniform acceleration. However, we can break the graph into distinct sections. In the first phase, the acceleration remains constant at -1 metre per second squared, so this interval is an example of uniform acceleration. In the same way, the acceleration is constant within the second and third parts. In general, if a section of an acceleration time graph is a horizontal line, then the object undergoes uniform acceleration. Next, it's important to understand that an object's change in velocity is equal to the area between its acceleration time graph and the horizontal axis. To see what this means, let's find the area enclosed by the graph in the first 10 seconds. The width is 10 seconds, while the height is -1 metre per second squared up. Since the area of a rectangle is width times height, we get -10 metres per second up. Overall, the lift's velocity decreases from 0 to -10 metres per second up. In acceleration time graphs, regions below the horizontal axis have negative areas, and they represent deceleration, or acceleration in the negative direction. Between 10 and 28 seconds, the graph coincides with the horizontal axis. This means the area is 0 and the change in velocity is 0. Accordingly, the lift travels at a constant velocity of -10 metres per second up for this entire section. The last section, from 28 to 38 seconds, is a rectangle with a width of 10 seconds and a height of 1 metre per second squared up. Therefore, it represents an area of 10 metres per second up. This positive value means that the lift's velocity increases by 10 metres per second in the positive direction. Resultingly, the elevator's final velocity is 0 metres per second. This makes sense because the lift stops when it arrives at level B12. Taking a step back, we notice that the lift starts and finishes at rest, so its overall change in velocity is 0. This brings us to another key point. If the areas above and below the horizontal axis of an acceleration time graph cancel out, the total change in velocity is 0. 12 floors below street level, Dylan showcases the Lexicorp's laser defence system. He boasts of its capability to neutralise threats, like the missile launched earlier this week. Given the hefty price tag on the high-tech equipment, Lotus replies that the government will need time to consider the purchase. With the tour now complete, Dylan guides Lotus out of the building. On the way, she spies a manila folder titled Anchuria. Without a moment's hesitation, she swipes the file and hides it inside her information package. It's bound to shed a light on Anchuria's involvement with the missile launch. Just as Lotus steps through the front door, sirens wail and shriek loudly. Drats! They were tracking the manila folder with an RFID tag. With guards approaching from every direction, she dashes towards the nearest station. Lotus weaves through the crowds and sprints up an escalator. A couple of bystanders block her path, forcing her to slow momentarily, allowing the guards to catch up. As they step aside, she makes a break for the platform, hoping to catch the 303 metro. This time, let's analyse an acceleration time graph of Lotus on the escalator. Here, up the escalator is positive, which means down the escalator is negative. Just like the previous example, this acceleration time graph is constructed from many horizontal lines. Therefore, we can break it up into multiple sections, and within each section, Lotus undergoes uniform acceleration. Initially, Lotus accelerates quickly at 1.4 metres per second squared up the escalator. Her velocity increases when she boards the moving escalator, and it increases further when she runs. From 2 to 7 seconds, Lotus moves at a constant velocity up the escalator, which means that she doesn't accelerate. From 7 to 9 seconds, Lotus decelerates or slows down to avoid running into the other passengers. Between 9 and 11 seconds, Lotus waits impatiently for the other passengers to move out of her way. Although she stops running, she continues moving upwards due to the escalator's motion. From 11 to 13 seconds, Lotus starts running again, so she accelerates in the positive direction. Finally, from 13 to 15 seconds, she continues running up the escalator at a constant pace. Now that we understand what each part of this graph represents, let's formalise the process for finding the velocity of an object at any point in time. Firstly, determine which velocity is already known. Is it the initial or final velocity? Next, mark the initial and final times on the acceleration time graph. Shade all areas enclosed by the graph, horizontal axis, initial and final time, then calculate the area of the shaded region. Finally, substitute all known values into the equation for the change in velocity. Let's see how this process works, step by step. Suppose that Lotus's initial velocity, before she boarded the escalator, was 0 metres per second. From this, we can calculate her velocity after 6 seconds. In step 1, we realise that we already know her initial velocity. Step 2 tells us to mark 0 seconds and 6 seconds on the acceleration time graph. Next, we shade the region between the graph and horizontal axis in the time interval 0 to 6 seconds. The first region is a rectangle with a height of 1.4 metres per second squared up the escalator and a width of 2 seconds. This has an area of 2.8 metres per second up the escalator. Between 2 and 6 seconds, the graph coincides with the horizontal axis. The area is 0, which means that the change in velocity is 0. Hence, the total change in velocity between 0 and 6 seconds is 2.8 metres per second up the escalator. Finally, we substitute the known values into the equation. The change in velocity is the difference between the final velocity and initial velocity. By solving this equation, we find that her final velocity after 6 seconds is 2.8 metres per second up the escalator. We can repeat this process for any time included within the graph. It doesn't need to be a nice, round number. For example, let's find Lotus's velocity after 11.3 seconds. We already know her velocity after 0 and 6 seconds, and we can use either of these points to get the correct answer. For the sake of this calculation, we will set the initial time to be 6 seconds, so her initial velocity is 2.8 metres per second up the escalator. Once again, we annotate the figure and calculate the area between the graph, horizontal axis, 6 seconds and 11.3 seconds. The rectangle below the horizontal axis has an area of minus 2 metres per second up the escalator. The negative area means that Lotus's velocity decreases. The last region has an area of 0.3 metres per second up the escalator. Consequently, her change in velocity is minus 1.7 metres per second up the escalator, and her final velocity after 11.3 seconds is 1.1 metre per second up the escalator. To recap, if you have an acceleration time graph and if you know the object's velocity at one point in time, then you can find its velocity at all other points in time. Back at the terminal, things are getting tense. Lotus sprints onto the platform as the doors start closing. She jumps through the gap, making it by a hair's width. She turns to watch the guards flood onto the platform and attempt to stop the train. Thankfully, the carriage lurches forwards towards the next station. Now that she's alone, Lotus can read the top-secret files. As a final example, let's analyse an acceleration time graph of Lotus's train trip. East is positive, which makes west negative. Just like before, we can break the graph into distinct sections. The train starts accelerating at 2 metres per second squared east, but its acceleration decreases gradually until it becomes 0 after 15 seconds. Since the acceleration changes, the train undergoes non-uniform acceleration. Between 15 and 45 seconds, the train is not accelerating. Therefore, it travels with the same speed and direction. From 45 to 65 seconds, the train's acceleration is minus 0.75 metres per second squared east. It decelerates and slows down as it approaches the next station. This time, let's use the fact that the train starts at rest to find its maximum velocity. Remember, regions above the horizontal axis have positive areas and represent an increase in velocity, while regions below the axis correspond to a decrease in velocity. Therefore, the train will travel at its maximum velocity between 15 and 45 seconds. Once again, we annotate the figure and calculate the area of the shaded region. This time, it's a triangle with a height of 2 metres per second squared east and a base of 15 seconds. Since the area of a triangle is half base times height, the change in velocity is 15 metres per second east. Putting this all together, we find the train's maximum velocity is 15 metres per second east. If you recall from our previous lesson on acceleration, the average acceleration of an object is the change in velocity divided by the time taken. Between 0 and 45 seconds, the train's velocity increases by 15 metres per second east, so its average acceleration is 0.33 metres per second squared east. In comparison, the instantaneous acceleration is the exact acceleration at a particular point in time. In this case, it varies from 0 to 2 metres per second squared east. As we can see, the average and instantaneous acceleration are not always the same. Let's pause here to discuss the types of questions you might be asked in exams. Questions will ask things like, draw an acceleration time graph. Describe the motion of an object. And extract information from an acceleration time graph. Before we finish, let's work through a sample question. A water bottle rocket begins on the ground, at rest. Its motion is represented in the acceleration time graph below. The water bottle rocket reaches its maximum height above the ground when its velocity is 0 metres per second. Calculate when this occurs. Pause the video here to think about your answer. Before we start answering the question, we should check the sign convention used. Up is positive, which makes down negative. We also need to understand what each section of the graph represents. Initially, the water bottle rocket is on the ground, at rest, and it accelerates upwards at 20 metres per second squared. Therefore, its velocity increases and it flies high into the sky. Next, the rocket's acceleration decreases as it uses up its fuel. It stops accelerating for a brief instant at 1 second. Between 1 and 1.5 seconds, the rocket's acceleration is negative. The amount of water and air ejected from the base of the rocket is not enough to overcome the strength of gravity, so it decelerates or slows down. From 1.5 to 4 seconds, the rocket accelerates at minus 9.8 metres per second squared. After running out of fuel, it accelerates downwards due to gravity. If you are ever stuck in an exam, you can draw diagrams like these to help you interpret graphs of motion. Let's take another look at the question. Our task is to find the time when the rocket's velocity is 0. But how is velocity related to an acceleration time graph? Remember, the change in velocity is equal to the area between an acceleration time graph and the horizontal axis. The rocket starts on the ground, at rest, and we are trying to find the next moment when its velocity is 0. Therefore, the change in velocity will be 0 metres per second. This corresponds to an area of 0, which is possible when the areas above and below the horizontal axis cancel out. In summary, our task is to find the time when the total area is 0. To make this easier, let's break the shaded region into 3 simple shapes. We can easily find the dimensions of both triangles, but we don't know the rectangle's width. The first triangle has a height of 20 metres per second squared up and a base of 1 second. Therefore, it represents an area of 10 metres per second up. The second triangle has a height of minus 9.8 metres per second squared up and a base of 0.5 seconds. Its area is minus 2.45 metres per second up. When combined, these two regions have an area of 7.55 metres per second up. If we want the total of all three regions to be 0, then the rectangle needs to have an area of minus 7.55 metres per second up. The rectangle's height is minus 9.8 metres per second squared up. We don't know its width, but we can represent this using the letter W. Since the area of a rectangle is width times height, minus 7.55 equals W times minus 9.8. Solving this equation for W gives 0.77 seconds to 2 decimal places. Putting this all together, we find that the rocket is stationary after 2.27 seconds. This is when the rocket reaches its maximum height above the ground. Let's revise what we've covered in this lesson. In the HSC Physics course, you will need to describe the motion of objects and draw acceleration time graphs. An acceleration time graph shows acceleration on the vertical axis and time on the horizontal axis. Negative values are possible since acceleration is a vector. If an acceleration time graph coincides with its horizontal axis, then the acceleration is 0. The object's velocity is constant, so it travels with the same speed and direction. Values above the horizontal axis correspond to acceleration in the positive direction, while values below the axis indicate deceleration, or acceleration in the negative direction. A horizontal line corresponds to uniform acceleration. A constant acceleration of 0 metres per second squared is also considered uniform acceleration. In contrast, if the acceleration changes, then the object undergoes non-uniform acceleration. The area between an acceleration time graph and the horizontal axis is equal to an object's change in velocity. Regions below the horizontal axis have negative areas because they represent a negative change in velocity. The average acceleration of an object is the change in velocity divided by the time taken for a given time interval. In comparison, the instantaneous acceleration is the exact acceleration at a particular point in time. We hope you enjoyed this Schooling Online production. For more easy lessons on physics, check out our first video on converting between graphs of motion.